morning.
Good morning.
Do I sound very echoey today?
Yes, you do.
Hmm. I wonder what is changed. Hmm. Yeah, I can hear my own echo too. Hmm.
Are you using a feedback loop?
No more than usual. So that's the weird part. Is that Um. Hmm.
Could be that it's not that something in the software might. Are you using OBS for the feedback loop or a different program?
I should not be using OBS for the feedback loop.
I'm
Let
sorry,
me.
did you say you were or you were not?
We're not. Should not be. Let me turn off the
Oh,
echo.
I was able to hear myself, which I shouldn't be able to. So it's capturing your desktop then. So it's capturing your audio feedback somewhere. You have to speak more. Well, I can't hear myself anymore, so
All right. So how about now?
it sounds good.
Okay. So I have to turn off my my mic monitoring. It's software based, so there's a little bit of lag. But today the lag is a lot more than usual, and I'm looking at the processor load, and it's no more than usual. So it's something was changed. I just have to kind of figure it out again. Maybe at some
Uh,
other time.
should also let you know that you're also very compressed now.
Very compressed.
Yeah, it sounds like you're speaking through like a 1980s megaphone.
Really? Huh. Okay. So something is not right about my audio setup.
So when you're talking normally, it's you're fine, but once you start talking softly, it's hard to hear you.
Okay. Um, okay, I can see sort of, how it might be an issue. I can increase the gain, that should be better, right? At least the voice is louder.
Louder, but the problem isn't the loudness; it's the picking you up when you're trailing off is the problem.
Hmm. All right. Well, I can't really spend too much time to work on this today. Not right now. Maybe at some other time, maybe later. Um. So we'll probably have just to we'll have to do it this way, for the time being. Um. I don't know how the YouTube side sounds. There's one person on the YouTube side, and I'm not sure how that sounds. I'm not gonna check that out either, because it's probably a good time to get started with the lecture. All right, so we got about four people on the Discord side and one person on the other side, on the YouTube side. Um, and I do apologize for the voice, not working out as well as usual. Um, So that's kind of baffling because I haven't really changed anything on that side. So what we'll do today is to get into the lecture that we kind of started on the other day, which is a big O, big omega, little omega, big theta, and little theta. So that's the module. This is the module that we are on right now. So I'm going to open it in a new tab. Okay, so the YouTube side sounds good, which is also weird because I don't think I did anything special on the Discord side. I'm just gonna check right now. Um, it does have automatic mic sensitivity turned on, and
The YouTube sounds compressed, but it's still better, slightly better.
okay, I'm gonna turn on automatic gain control on the Discord side. All right, so that's probably the extent that I'm gonna tweak things today. All right, so on the other day, which is a week ago, we talked about section two. So that basically talked about why it is important to talk about time complexity as far as algorithms are concerned. And what we'll do today is to move on to, uh, okay, that's not good. Discord just crapped out, so I'm gonna have to restart in Discord. All right, so there we go. Discord just crashed, so I'm gonna have to go back to screen share again. All right, things are definitely not working smoothly today. There we go. All right, so we'll continue. So last time we talked about algorithm time complexity, and what we'll do today is to actually get dig into the nomenclature, the names of various things. Basically, these are all definitions, but they can be very confusing. We got started last week, okay, on the asy- asymptotic characteristics. I think we briefly talked about supremum, and that's what we'll do today again is to talk about supremum. The one of the things that relates this topic with relations is it does require a partial order. In other words, if set A has a partial order, then we can define supremum, for elements in the set A. So we'll basically use the less than or equal to as a relation for A, the Cartesian product between A and A. Or I should say, the relation is a subset of A cross A. And we already know from the discussion of relations that partial order requires something to be a relation to be reflexive, antisymmetric, and also transitive. Now, the actual less than or equal to relation in integers and real numbers is also total ordered, but we don't need total ordering in order to define supremum. And that's also why there's that potentially there are more than one solutions for supremum because of partial ordering. All right, so what we do is now we take a subset x is a subset of A. And what we do is we define a predicate. Okay, so I'm just going to highlight what predicate we are talking about. So this predicate is indicating that y is greater than or equal to everything in the set X in the X set, which is a subset of A. So let's make sure that there's no question about this part. Okay, and Aaron is typing, and I'm gonna wait a little bit until the. Oh, okay, Omar is typing too. Shouldn't little be capitalized in the title?
Of the big, little,
Oh,
omega, theta.
oh. um, I mean, as a title, I suppose it should be capitalized. And Omar says, why do we need to take a subset? Can't we just use A? That's interesting because we do not want to define the entire A. We just want to use a subset of A for the time being. And the reason why this is the case is because we are going to use supremum later on. Um, that will actually include everything. So we just want to use a subset for the time being. All right, so it will be kind of clear why we want to use a subset when we get to limit of sequences. And particularly when we get to limit superior and limit inferior, that is when why the subset concept is useful. So for the time being, we'll just say that we take a subset X of A. Now X can be A, it's just that it has to be it cannot have anything other than A already has. Okay, that's basically the bottom line. Um, and then the predicate in return is used in the definition of supremum. Supremum. So S is the supremum of in X, and the definition of S, which is the supremum, is the first thing is we want to make sure that um, the element S is quote unquote one of the maximums if there are multiple maximums in the set X. Okay, so that's the first requirement. The second requirement is a little bit more confusing because it uses it uses a quantifier, a universal quantifier. So now we are looking at all the S primes, and each S prime is kind of by the definition of P, is also an upper bound of X. So S prime is also an upper bound of X, but we want to make sure that S, which is what we are trying to qualify out here, um, is less than or equal to S prime. So we are looking at a whole bunch of, we're evaluating a whole bunch of upper bounds, and we're looking at the smallest of the upper bounds. All right. So are we doing okay so far with this concept that we are looking at the lowest of upper bounds? Okay. I'm not seeing any questions here. So the reason why we might have sort of, okay, it is sort of, but not necessarily, because there's no because y doesn't have to be in x. Okay, because there's no restriction of where y is coming from, so y doesn't have to be in x. So y can be in a in general, but not in the subset of x. So that is the kind of the tricky part, because now let me just kind of play with my new tool here. So this is my new toy. Well, okay. Last time I showed how to use this toy already. It's my Remarkable 2 tablet, but I didn't find a really good way to capture my handwriting. So this time I think I found a better way to do it. So what we can do is we can define. Oh, it has gone to sleep, so I'm gonna have to wake it up again. Um, Give me a second here. All right, so let's see if this works. Yep, it's working. All right, so we can define the set A to be 0, 1, 2, 3, okay? And then we can define the subset X to have just 0, 1, just those two. So now, what qualifies as the upper bound? There are three elements that can qualify as the upper bound. So we can now say P of 1x is true, P of 2x is true, and then P of 3x is true as well. So we can see how there are three elements that all fit the qualification of being the quote unquote upper bound of x. I mean, one is pretty obvious, right? Because one out of 0 and 1 in x is really the maximum, so that makes sense. But 2 and 3 are also upper bounds because they are larger than or equal to everything that is already in x, and the relationship greater than or equal to is already defined because we basically say that set A has a greater than or equal to or less than or equal to relation, so that we can relate everything. So is that okay? I mean, does everybody understand this portion of it? All right. Okay.
What are
So
we equaling? Hold on. So is t supposed? What is t supposed to be again?
um,
Your example. The p of
P
1, 2, 3 of x. Two.
P is a predicate. So P is basically a predicate. You can look at it as a function that returns a Boolean. So P
Okay.
of yx, y is an element of A, x is a subset of A. So P of yx is true if and only if everything in x, every element in x is less than or equal to y.
All right.
So using this particular definition, and we go to here. So just to make this more complete, the P of 0x is false because 0 is not every element in x or is less than or equal to 0. And that's why p of 0x is false. Is that okay? All right. All right. So assuming this is okay, we're going to move ahead. So of all of the upper bounds, okay, so let's go ahead and define the upper bound, the supremum in this case also. Um, cannot copy the LaTeX from equations anymore. You mean from the notes here? Oh, okay, that's because this was generated before I made a change to the script. So if you look at the date, this was generated in April 22nd. I know some of you want to kind of be able to copy and paste it. So give me a quick second here so I can show you. I can do that part too. Just give me a second. And this is 00282. Publish lot module dot tech. There we go. Because I changed the tool, or the configuration of the tool that generates the HTML equivalent document. So the old way of generating things does not include the LaTeX code, and the new way does. So it should be updated now. So when we right click and then show math as, now it shows the LaTeX commands too. So that's a fairly easy change here, but I didn't regenerate the HTML code for this particular one. All right, so I do apologize for a little bit of a um, distraction here. So now we want to look at the supremum of x, in the example. So in the example here, now we want to ask, what is the supremum of this x? Okay. So remember, this is also basically is asking, what is the minimum? What is the minimum of all the upper bounds of x? So when we look at the upper bounds, this is an upper bound, this is an upper bound, and so is this one. So of all the upper bounds, the one that is the smallest is 1. So there we go. So the supremum in this case of x is 1. Now you might look at supremum itself like, no, so that's basically the maximum. Well, that is not the case either, because if we have only a partial order, the supremum of a particular set can be a set itself and doesn't have to be a particular value. So supremum of x is technically you know um, a set of 1 in this case, and it is not just 1. But with integers and real numbers, the supremum is basically the same thing as the maximum in a set. All right. So part of the reason why I define supremum like this, has to do with um, you know, it's also mathematically how it is defined. Okay, so now we have Infinum, which is basically the opposite of supremum. So Infinum, I use the predicate q, y, x in this case. So q, y, x is basically saying that y is the lower bound of x. So if you compare the notation, yeah, I switched the notation, because I use a colon here, for the quote unquote such that, and over here I use parentheses, but they really mean the same thing. So the only thing that is different between the definition of P and the definition of Q is how I specify x is less than or equal to y in the definition of P, and I use y is less than or equal to x in the definition of Q. That's the only difference between those two. So
What
what
does the colon mean?
the colon means such that. So
Okay.
it really means the same thing as this one over here. It's just that when I switched the notation, I forgot to update some of the notation. So this one kind of was using the old notation. But they really mean the same thing. Are we good so far? All right.
Sounds good.
All right. So So that means when we define the infimum of x, it is the largest of the lower bounds of x, which to us, when we think about integers and real numbers, the infimum of x is really the same thing as the minimum of x. So you can kind of make the rough equivalency between supremum and maximum and infimum and minimum. Okay, so you can sort of make that association. That association works for integers and real numbers, but it doesn't work in general because A doesn't have to have a total order. It only needs to have a partial order. But in terms of computation time, how much time it's going to take to compute something, we're working with real numbers. So as far as we are concerned, in this context, in this limited context, you can look at supremum as maximum and look at infimum as minimum. So now we get to section 3.3, and we're going to go through the paragraphs one by one. So now we want to look at the limit of a sequence of numbers. This is partially why pre-calc is important, because I think in pre-calc, maybe in calculus 1, but I cannot remember which one, but one of the calculus classes talk about the concept of limits. Does someone want to remind me which math class introduced this
Calc
concept?
one.
Calc 1? Okay, thank you. So in this case, the concept of limit is not quite as weird as the one in calculus, but it is still the concept of a limit. So I'm going to spend some time to explain it because the prerequisite of this class is pre-calc and not calc 1. So that means some people may not have taken calculus, calc 1. So I'm going to spend some time to talk about this one. So when we talk about the limit, okay, so if we have an infinite sequence, okay, x1, x0, x1, x2, all the way up to there's no end to it, right? That's why it's called an infinite sequence. So the question is, if I just look at if I look at the limit where I approaches infinity, and I just want to look at x of I, what does it mean when we look at the limit of a sequence? Okay, that's the question. Okay, so now obviously, if you have a sequence where x of I is 2 to the power of I, or I to the I squared or something like that, then this is sort of meaningless because as the number in the sequence gets larger, the value goes larger as well. So in that case, it doesn't have anything that we're interested in because it's undefined. The limit goes to infinity too. So what we want to do is to kind of look at this notation here. I know this looks really like, whoa, what is this? There's a lot of stuff going on, right? So what we want to do is to understand a multi quantifier or nested quantified statement. We kind of make it makes sense to go from the outside in instead of the inside out. So we'll look at each one step by step. The first one, or the outermost quantifier, is basically saying for any epsilon that is greater than 0, and we want epsilon to be a real number. So that is finding what epsilon is. So basically we're saying just pick me a number, an epsilon, and as long as epsilon is greater than 0, the following should be true. Okay? So there's not really a whole lot of restriction on what epsilon can be, other than it cannot be 0 and it cannot be negative. Otherwise, we can pick any real number that is greater than 0, and we want what is inside the parentheses to be true. So yeah, so you can pick epsilon to be really big, but you can also pick epsilon to be very, very small. Okay, you can pick it to be like 0.01, but you can also pick it to be 0.00000001. And you can keep going as long as it is not 0 itself. It can be a very, very small number, and whatever is in the parentheses still needs to be true. Okay, so that's what epsilon is. And then the next item is there exists an m as a natural number. Okay, so we start with a for all. Okay, we basically say pick any epsilon that is greater than 0, and epsilon has to be a real number. And then for that specific epsilon that we have picked, there has to exist a particular m, which is a natural number. Okay, what about these two? So by the time we get to the innermost part of this quantified statement, we have already bound a particular epsilon, and we basically say we should be able to find an m such that, okay, so now we look at the following, such that for all j that is greater than or equal to m in natural numbers, k minus x of j, when you look at the absolute value, that has to be less than epsilon. Okay, so this is this looks this is kind of strange, right? Okay, so I
Uh,
think, yeah, go ahead.
for the epsilon greater than 0, so the whole epsilon greater than 0
Mm-hmm.
within R, right? So shouldn't there be a parenthesis around the epsilon and the 0 to indicate that we're... So like to me, like reading that to me, it looks like we're taking for all 0 of real numbers, and that just looks a little confusing.
Oh, okay. This is basically for all epsilon that is a real number and it is greater than 0. So I'm just kind of stringing a few things together, so that it's, I was hoping that this is easier to read, but basically it's both indicating where epsilon can come from, and also the restriction that epsilon has to be greater than 0. Same thing over here. J is a natural number, but j also has to be greater than or equal to m.
Gotcha.
All right. So now that we have three levels of quantification, what exactly is the actual statement? Okay, what is the actual comparison? The actual comparison is to say, if I, k minus x of j, and remember x is a sequence of numbers, so x of j is a particular value in that sequence. That has to be less than epsilon. And that has to apply for every j that is greater than or equal to m. So if I can find such a value k, that is a unique value. Um, that is it's basically the limit in this case. It basically the k over here is the k over here. That is the limit of x of I. All right.
Is that the absolute value of k minus x sub j, or is that the cardinality of k minus
Oh,
x sub
this is
j?
the absolute value.
Okay.
This is an absolute value because k is an element. Because k is an element and x of j is also an element. So this subtraction is not a set operation. It is a real number. Is a real number operator. So that means we have a real number here, but with a real number, we can apply the absolute value so that we can define epsilon to be just kind of okay. I think it's best to use a picture. Okay, so let me just use a picture to represent this. So we'll switch to the remarkable page here. So if I were to look at the picture, okay, so we can use this here to be the value of x of something, and then the horizontal axis here is basically I. Okay, which number in the sequence are we looking at? So the idea is to say the sequence, each value in the sequence can go up and down and up and down and up and down and so on, but eventually they all have to converge to a particular value. So let's see what we mean by epsilon. Okay, and I want to see if I can use a ruler in conjunction with the tablet. So I'm looking for, sorry for the noise as I look for a ruler. And of course, when you need one, you cannot find one. That's part of Murphy's law, I suppose. Oh, I got one. It's a lot bigger than what I need, but it's gonna be okay. So what we'll do is we're gonna pick a larger epsilon first. Okay. So we'll go ahead and pick an epsilon so that let's see. Yeah. So we'll go ahead and look at okay. That's not good. Sort of. Okay, so go ahead and pick up this epsilon for the time being. This is our epsilon, okay? So, and this is our k. So let me use a ruler. This is our k over here, and this is our epsilon. So what we want to know is to say, well, starting from where in the sequence can we guarantee that all of those values or at or after that sequence will meet the requirement of within epsilon of k. So in this case, okay, I know my picture may not be the best, but I'm going to pick this one here. So I'm going to say, hmm, I can pick a value of m here so that if I look at all the x something but past x of m, all of those are going to be within plus or minus epsilon of k. Is that okay? Does everybody understand what I'm saying? In other words, in this case, uh, just turn on something that I do not intend. Okay, so in this case, I'm just drawing a line of k for the time being. So if I draw this line here, yeah, I know it's not the best representation, but let's just say that that line is representing k in the x-axis. Okay, so you can see that every element of x in the sequence of x past m is going to be within epsilon away from k. All right. So the idea is okay, but that epsilon is pretty big. What about the smaller epsilon, right? So let's go ahead and pick up a much smaller epsilon. So what we'll do is we will pick up an epsilon here, and then we'll say this is our epsilon. Okay. So now, when we look at that as an epsilon, then we ask the question again: can we find a value of m such that every element at xm, xm plus one, xm plus two, and so on, they're all within k plus or minus this particular new epsilon. So now the answer is yeah, sure, we can do something like that because if we say let's go ahead and pick this one as our new m. So we're going to say this is not the epsilon, this is not the m that we're using, and we are looking at this particular epsilon and this particular value of m. Then we say, oh, okay, even though we make epsilon smaller now, I can still find an m as an integer as the starting point of the index so that every value of x in the sequence is going to be within k plus or minus epsilon within that range of values. So the idea of a limit, okay, let's go back to the limit concept here. So the idea of this limit here of saying uh, you know can we reduce epsilon even further? The idea is in order for the limit of k, the limit which has a value of k to be defined, I should be able to pick an epsilon that is even smaller or as small anything that is greater than zero. Okay, I can pick an epsilon that is anything greater than zero, and still be able to find an m in n such that everything past x of m is within k plus or minus epsilon. Is that concept okay? The other way to say this is to say x of I converges to the value of k. Are we good so
Well,
far?
we're gonna have to think about it longer than the class is going to enable. So for now, yes.
Okay. So you can um all right. So if I go back to the picture, and I can upload the picture later on too. So you can basically see that the function or the sequence itself doesn't have to be monotonic. It doesn't have to be always increasing. Doesn't have to be always be decreasing. It can go up and down, but I have to be able to say, hey, give me any epsilon, and I just have to move this m further down in the sequence. But I can still guarantee that everything past that point is going to be k plus or minus epsilon. Is that okay?
Yeah, that makes sense.
Yeah. So that if that condition can be guaranteed, then we can say this exists. Okay, this k does exist as a as I approaches infinity, x of I is going to is k. It has a value of k. Now does do we have to find an x of something so that its value is exactly k? Nope, doesn't have to be. Okay. In other words, if we look at every single value in the sequence, even though the sequence is infinitely long, none of those need to be exactly k. Okay, but as we decrease epsilon, then they are getting closer and closer to k from either side. So that's basically the idea of taking the limit. All right. So now the question is, can we define a sequence such that this limit does not exist? It's pretty easy. If we define x of I to be -1 to the power of I should put parentheses around the -1 because it's -1 the whole thing to the power of I, then the limit does not exist because it just flips between 1 and -1. And as a result, I cannot just say, okay, I'm going to pick an epsilon like 0.25. Okay, where is the m so that x of m and further away is going to be within, a certain within k plus or minus epsilon. I can I cannot find such an m, and as a result, the limit does not exist. So if we go back to the graph, okay, because I think it's kind of helpful to look at it from the graph's perspective. So, and I can scroll down here because I can use the other portion of the space. So if I get down here, and I'm going to draw another picture here. This time I'm using a ruler, so things are slightly more aligned. Okay. So this is the value of each number in the sequence. Here's -1, here's 1, and this is basically the index I. And this time I can even say, let's look at this as index 0, index 1, index 2, index 3, index 4, and so on. I don't even have to go very far. You guys will get the idea, okay? Because when we're looking at -1 to the power of 0, the point is here. When we look at -1 to the power of 1, that point is here. So we can see that it just keeps oscillating between 1 and -1. Okay. So now if I ask, okay, I want to pick an epsilon of 0.25, where is that m so that everything, at m or and past is going to be, plus or minus 0.25 from a particular value of k? Is there such a value k in this case? And the answer is no. I cannot find it, okay? Because it simply does not exist. So is that okay? Does everybody understand why when x of I is defined to be -1, the whole thing to the power of I, the limit does not exist? Are we good so far?
Yeah.
Okay. So that is not good, okay? Because there are certain functions, in the estimation of time complexity, that it might oscillate, okay, between two values, and it never really settles, and it doesn't converge to a single value. Hmm. And what are we going to do? So what we're going to do, well, there's one more thing that we have to define first, okay? So we're going to define, the limit of a sequence can be infinity. So it is written like this in this particular format. So I know that infinity is not a value, but we can define the limit to basically be infinity, and this is the definition, okay? So when we say the limit when I approaches infinity of x of I is infinity, what we are really saying is for all value of y in a real number, there exists an m in n such that for all the values of j greater than or equal to m as a natural number, x of j is greater than y. So instead of converging, to a particular value, we are basically saying, okay, pick any value y, and I should be able to pick. I should be able to find an integer, a natural number m, so that all the values in the sequence past m are going to be more than. It's going to be greater than. It's going to be greater than y. All right. In other words, you can find me a really big value, y here, and I would say, well, guess what? It's not the largest one because everything past this particular m are all larger than the value that you have given me. That is how we define the limit of a sequence to be infinity. Is that okay?
Yeah, that makes sense.
Okay. All right. So now we try to solve the problem. Okay, we're trying to solve the problem of, okay, but what if something is oscillating? Okay, then what can we say about it? So the way we can do it is to define a what we call the limit superior. So this is really weird, okay, because the limit superior. Let's look at the definition. So the limit superior of a series or sequence of numbers x of n is defined like this. We are taking a limit again, and this time the limit, n is approaching infinity again. And we are looking at the supremum of x of n. Hmm. Oh, okay. So the supremum, so this definition is in return, this is how we look at that. And there are two, it's a nested set notation. Okay, so we want to look at the set notations from the inside out. Okay, so we want to look at the inside first. So in the very inside, we have x of k for k greater than or equal to n. So we are looking at the set of values, okay, of every number in the sequence that has an index that is greater than or equal to n. In other words, we pick a particular value n. If you want to look at this particular notation, we pick a value of n, and then we just say x of n, x of n plus 1, x of n plus 2, x of n plus 3, all the way down to all the values in the sequence. That is in this particular set, and that's why we use the curly braces to define a set. So what are we going to do with that set? We find the supremum of that set. Now we have already kind of talked about the supremum is kind of like the maximum. So we are basically finding the maximum of the subsequence of values starting at index n. Instead of starting from 0, we are starting at index n. So what about that? Okay, so we can see how the supremum of this particular set is a single value, and then we say, well, what about n itself? What is n? So we have n being greater than or equal to 0 here. So we basically look at all the values of n. N is an integer that is greater than or equal to 0. We will basically define one value for each value of n. So when n equals to 0, we find the supremum of basically the entire sequence. When n equals to 1, then we find the maximum starting from x1. When n equals to 2, then we find the maximum starting at x2, and so on. That is, and then we look at all of those particular values, and then we find the infimum, or basically the minimum of that. All right. So I know this sounds really, really confusing. Okay. So what we'll do is we're going to use an example. And let me switch to a new page on the tablet. And this is not going to refresh, because it's actually just capturing the pen movement. It's not actually reflecting the page itself, and that's why it's so responsive. But I can always just refresh it. Okay, it's not gone. It's still on my tablet, so I can just upload everything on the tablet today. At some point to um, the Discord channel. Okay. So what we'll do is we will define a particular sequence first, okay? So because we want some concrete values, right? So the concrete value we are going to use is to say x of I is by definition 1 divided by 1 plus I, okay? I originally wanted to use 1 divided by I, but that won't work, right? Because the sequence starts with I being equal to 0, and 1 divided by 0 is undefined. So I'm going to use a 1 plus I as the denominator. So as you can probably see, okay, so this is a fairly boring sequence because x of 0 is 1, x of 1 is basically 1/2, x of 2 is 1/3, x of 3 is 1/4, blah, 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 blah. Okay? Not a very exciting sequence at all. However, it is a sequence that we can say, okay, what can we say about this particular sequence? So let me go back to the notes because I want to copy the definitions that is in there. Specifically, I want to copy this particular definition. And there's no easy way for me to copy and paste onto the tablet at this point because the tablet is really disconnected, in this way from the browser. So I'm just gonna copy in the entire thing, which is this expression here. So we are looking for the infimum or the minimum of the maximum of x of k such that k is greater than or equal to n, and then we collect all of those maximums, and then we find the minimum of those maximums. Okay. All right. So now we are ready to go back to the tablet. Okay, because I just copied that. Okay. So what we'll do is we're going to say, let's see what happens when n equals to um, 0. Okay, so for the case n equals to 0, then we are concerned about the supremum of xk. K is greater than or equal to 0. And can anyone tell me what that is? What is the maximum starting from? Yeah, go ahead.
A 1.
Exactly. Okay, so this is 1. What about when n equals to 1? Okay, then we are looking for the supremum or the maximum of x of k such that k is greater than or equal to 1.
1/2.
1/2. Okay, very good. And n of 2. I mean, you guys get the idea already. This is going to be a 1/3, and so on, right? So now we take each of these supremum, okay? We take each of these supremum and put it into a set, okay? So now we can see, okay, if we put all of these things into a set, that set is going to look like just 1, 1/2, 1/3, 1/4, blah, 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 like that. And it's going to be an infinitely large set. And none of the elements in this particular set is 0 itself, okay? But now we are looking at the infimum or the minimum in this particularly infinitely large set. And what is that going to be?
Sorry, could you repeat?
Okay, so we are looking. Okay, so I. Okay, first of all, are we okay with these three
Oh,
statements?
it would be 1 over a great number, so it would be 0.
Exactly. All right. So now we can now say the limit. Um, okay, I have to go back to the notation. Oh, that's the wrong one. So now we can say the limit supremum of this particular sequence is 0. Okay, limit supremum of x of n when n approaches infinity is 0. So let me go back to the tablet page. So now we know that is 0. In other words, when we look at the minimum of the maximums, as we consider the subsequence starting at different points, starting with the index of 0, the index of 1, index of 2, index of 3, um, the overall minimum is actually 0. As n gets larger and larger, we get closer and closer to 0.
Is that for all x of n, or
Say
just
that.
for this x?
It's for this particular sequence.
Gotcha.
So I think this is the limit supremum of x. So the limit supremum of x is that. All right. So remember, this was kind of devised so that we can deal with x of I being defined as -1, the whole thing to the power of I. So let's take a look at that one and see whether there is a limit supremum defined for that particular sequence, because we know there's no limit defined for that sequence. But is there a limit supremum defined for that particular sequence? So, I think I used the wrong term. Is the limit superior, not supremum, the limit superior. So is that defined for -1 to the power of I as I goes to infinity? That's the question. So let me just kind of copy that first, and then we'll take a look at the actual computation of this. All right, so I just copied it. Now we can go back to Remarkable and find out, okay, so what do we do with this? Okay, this is the new thing that we were trying to solve. So we know this can be rewritten as the infimum of the following. The supremum of x of k such that k is greater than or equal to n. Each one is a number, and then we want n to be greater than or equal to 0. Okay, so I'm just copying this. You can see how this here is really the same thing as this over here. Okay, because it's the same definition. The only thing that has changed is what is x of k, right? So now we say, okay, let's lock n down to 0. So when n is 0, okay, we want to ask what is the maximum of x of k such that k is greater than or equal to 0. Okay, I'll let you guys try to answer the question. In other words, if I start from index 0 and I look at x of I, okay, uh, such that I is greater than or equal to 0, what is the maximum of those? When, um, okay, this is when x of I is defined to be -1 to the power of I.
Oh,
Is it
0
one?
would
It's
be
going to be
1.
1, exactly. Okay, so this is 1. What about when n equals to 1?
-1. It should be
Exactly.
Negative one?
-1, 1, -1.
It's going to be 1 because we're looking at the maximums, right? So changing the
Oh yeah.
starting point doesn't do a single thing, because because remember the sequence just kind of flip flops between 1 and -1, so it doesn't really matter where we start. The maximum starting from that point on is always going to be 1. All right, so when n equals to 2, the supremum of k is greater than or equal to 2 in this case, is also 1. Oh, okay. So that means if I look at the infinitum of all of these, I'm really looking at the infinitum or the minimum of a set that has a whole bunch of ones. There's a, well, actually, I take it back. I cannot have that, can I? Because it's a set. It really is just that. Okay, this it doesn't work. But basically, I just crossed out this whole bunch here. The set only has a single value of 1. When you have a single value, the minimum is going to be that value itself. So that's why the limit superior of -1 to the power of I is just 1. It is defined. So what is that saying? How is this? What is this contrasting? It is contrasting the fact that x of I, when okay, I should say -1 to the power of I, it has no it has no limit. Okay, if when you look at the sequence has no limit, but it does have a defined limit superior. Okay, and this is how we solve the problem of what if we have a sequence where it kind of keep flipping and flopping between two values, and it doesn't really converge to a particular value. We say that's okay, as long as you know the flipping and flopping has its own envelope, it's okay. So we just need the flipping and flopping to be contained within an envelope, and the envelope itself is quote unquote, I guess, it converges to a tunnel. Okay, so we are starting with a really wide funnel, and then as we go on, the funnel gets smaller and smaller, and then at some point it becomes just a straight tube where all the values, after that point is they can keep flipping and flopping, but the flipping and flopping will not exceed that particular value. That's how we are defining limit superior, and limit inferior is really just the opposite. So let me look at this from a more graphical perspective, because I think the graphical perspective is going to be helpful. So I'm just making a new page first on the tablet, and then from here we can just refresh the screen. So what I'm saying is, if I have a function where things get flipping and flopping, but as long as the flipping and flopping, converges, or it does not exceed a certain amount, past a certain point, we can still see that. Okay, so what limits superior is asking is, if I look at the maximum, okay, starting from different points, so we can see the maximum starting from this point is this value. So for all of these values, okay, for all of these values of x, the um, uh, the maximum starting from these points is going to be here, okay, for all of these guys over here. Um, but mm, from this point on, okay, so if I look at all the points, let me see, let me think. Okay, so from this, hmm, I would say from this point on, okay, so from this point on, okay, the maximum is going to be this point here, because that's established by this point over here. And then from this point on, okay, if I look at this point and on, then the maximum, from this point on is defined by this single point, so it has a maximum of here. But when we look at these points, this is a maximum, this is a maximum, this is a maximum, this is a maximum. I'm looking at this one here. There's a maximum, this is a maximum, and so on. So when we look at all of these maximum, and then we say, but what is the minimum of all of these maximums? as long as that minimum of the maximums starting from different points is converging, then we still have a limit superior defined. Now, what about the limit inferior? It's exactly the opposite. Okay, so if we ask, starting from this point over here, what is the minimum, okay, of the entire sequence? We go like, well, that's defined by this thing here. So, from the perspective of n equal to zero, we have a minimum, of from that point on is here. Um, and then when we look at the perspective of this particular point here, and we ask, so what is, okay, I think picked up, well, I suppose it's okay. So when we look at this particular point here, and we ask, what is the minimum starting from this sequence, starting from this index in the sequence, the answer is, well, it's over here, okay? Um, then we look at the perspective of this particular index, okay? So we look at that particular index in the sequence, and then we ask, from this index on in the sequence, what is the minimum? We go like, well, it's kind of here because it's defined by this point. And Ben and Joshua is making a statement, kind of like, I'm not familiar with Rayman sums. Um,
Yeah, it's similar concept in calculus too.
oh, okay. All right, so maybe it's the same, maybe it's not. I cannot know for sure because my calculus is from 35 years ago, so that's a long time. Um, but when we look at things from this particular index perspective, the minimum is defined by this point. So the limit inferior is looking at all the minimums, okay? And then we ask, what is the maximum of the minimums? So we can see there's a general trend, okay? These things, seem to, settle at a certain point. And then when we look at all the minimum of the maximums, they also seem to kind of converge at some point. So um, as long as we can define an envelope, okay, you know, within which the fluctuations can occur like forever, we will still be able to define the limit inferior and the limit superior. So the whole idea of limit inferior and limit superior is basically to say we don't need a limit, okay? The sequence itself does not have to converge. We just need to contain the fluctuation of the sequence. RMS has to do with, yes, RMS has to do with the area under a curve, and it can fluctuate. And RMS is used a lot in power calculation in electrical engineering, which I know nothing about. I think it's, is it root mean squared RMS?
Oh, I think we're talking about Riemann sums.
Oh, okay. Oh, okay. So it's a different RMS then.
Oh, yeah, yeah.
Yep. Because in electrical engineering, there's also a RMS. Okay.
I was just lazy and I didn't want to type out Riemann sums.
Okay. All right. So, but we are not concerned about the area. We just need to define the envelope. Okay. As the sequence goes on and on and on, can we describe the behavior of the sequence? That's all we want to do. There's no calculation of the area. There's no calculation of the different of the derivative, along the curve, because as far as we are concerned, there's no curve. Okay, because curve only exists when we are talking about a continuous function. A sequence is not a continuous function. Okay, because it's each one is a discrete value, and you already know in calculus, okay, if it's not a continuous function, you can't really quite define the derivative. Well, at least at certain points, it does not exist. So now we have limit inferior, we have limit superior. So now we want to look at upper bound. So we are finally getting into the big O notation now. I'm just looking at the time. Okay, we still got about 15 minutes. So this is good, okay, because I would really like to at least get to one of the big O or little o or big omega, little omega, notation. And seems like we can. So we look at the big O notation, and this one is not a it's not me mistyping something. It really is an element of. Okay, so the big O notation is actually giving you a set of functions. Um, and when we talk about big O of g of n, okay, now so f of n and g of n are basically two functions, and in this case n is a natural number. In most cases, okay, when we try to describe the characteristics of the time complexity of an algorithm, n is a natural number because the problem size typically is a natural number. Now, does it mean that all computational problems have the uh, quote unquote size of the problem being a natural number? Maybe not all the time, okay? But most of the time, n is just a natural number. So we have f of n giving us a real number. We have g of n giving us a real number too. So f of n and g of n can be just about anything, okay? So when we say that f of n is an element of big O of g of n, what does that mean? This is a if and only if, otherwise known as, okay, that means the following, okay? It means the limit superior of f of n divided by g of n and taking the absolute value of that is not infinity. That's all it's saying, okay? It is less than infinity, which basically means it can be a specific value. It has to be a specific value. Can it be zero? Yeah, absolutely. It can be zero. Can it be one? Yep. Can it be 22.5? Sure. Can it be 6,731.25? Yep. Can it be pi, which is an irrational number? Sure. Not a problem. As long as it is not infinity itself, we can use this notation. All right? So, all right. So let's go through some examples of this big O notation, because in quote unquote common literature, I think the big O notation is misused a whole lot. Okay, because let's check out a few things. Okay, so what we'll do is we are gonna use here, and then we'll check out a few things. So we'll define f of n as x to the power. Oh, sorry. It's not what I meant, and there's no undo in this case, so I'm gonna have to cross out stuff now. So we'll say this is n squared, and then we'll say g of n is n cubed. Okay, so we can definitely tell that in this case f of n is gonna grow a bit slower compared to g of n. So now the question is, what about this? What about the f of n is an element, okay, it's an element of big O of g of n. Okay, this is a question. Okay, we want to answer this question. So what we want to do now is to look at the absolute value of, okay, so let me go back to the definition. So we want to look at the absolute value of f of n divided by g of n. And we say, what happens when n approaches infinity? What's going to happen to that thing? So we go back here and we say this is f of n divided by g of n. We look at the absolute value. So instead of using all of those kind of confusing terms like limit superior, limit inferior, and stuff like that, we'll just kind of lock n down to something. Okay, so we'll say when n equals to 0, um, f of n divided by, oh, that is undefined, isn't it? Okay, so we'll kind of skip that one. We basically have to say the sequence, basically starts with index of 1, but that's okay. So f of n divided by g of n is just 1 when n is 1. When n is 2, then we have 1/2. When n is 3, then we have 1/3. When n is 4, then we have 1/4, and so on, right? Because hey, after all, f of n divided by g of n is really just n squared divided by n cubed, which is, yeah, what boils down to just 1 divided by n. All right, so now when we say, what happens when n approaches infinity? What are we looking at? Oh, you guys cannot see it. Let me scroll down. So when n approaches infinity, what are we looking at? This, okay, this, it doesn't capture that part of the screen, so I'm gonna have to write it here. When n approaches infinity, what are these values approaching? We start with 1, then we have 1/2, 1/3, 1/4. So when n approaches infinity, what is the limit?
0.
Just
Yeah, exactly. It becomes 0. So now we can say the limit superior of, um, f of n divided by g of n, and we just look at the absolute value, that is just 0. Okay, but what does that mean? It means it is, okay, so now you have to ask the question, is 0 less than infinity? Yes. Okay, so if 0 is less than infinity, and that is the limit superior of f of n divided by g of n, or the absolute value thereof, then we can say, oh, this is not a question anymore. It is true. Okay, so can we explain this in English? That was actually one of the comments that I got from my dissertation committee when I was in graduate school. Was the 3 professors on my committee said, "Jack, can you explain this in English?" Okay, sure, absolutely. All this is saying is n cubed is an upper bound of n squared. That's all it's saying. Okay, all right. If that is the case, okay, we have a lot of f of n that would become elements of big O of g of n. Okay, so let me open a new page and refresh.
so for this one, if g of n is greater than the f of n, that would make the g of n superior to f of n.
It will it will make the limit superior 0. If g is growing faster than f, and it is, well, okay, it's difficult to define, what is growing faster, because there's the linear growing faster and then the non-linear growing after. So let me define, this one over here. So if I define f of n to be um, 1/2 of n cubed, and I define g of n as just n cubed, then, in this case, f of n is also an element of big O of g of n. Does that make sense? Because n cubed is still an quote unquote upper bound of f of n, sort
Right.
of, right? But if I flip it, it still works, because if I define f of n to be 1,000 of n cubed, g of n to be just n cubed, it still works. Okay, f of n is still an element of big O of g of n in this case, because the value basically, it's 1,000, right? When you look at the limit superior, it really is just 1,000. Now the question is, well, 1,000 is not 0, but is it less than one? Is it less than infinity? The answer is yes. 1,000 is less than infinity. It is a particular real number, and it is not infinity. Is that okay? So now we can say, okay, what about a constant time algorithm? So f of n is just 1, okay? And g of n is still defined to be n cubed in this case? Sure. N cubed is still an upper bound of f of n in this case. So you can see that, oh, just because we know something is big O doesn't seem to say a whole lot, right? Because I can now say, oh, guess what? the bubble sort algorithm, which is not really efficient, I can say it has a big O of um, n to the power of fourth. Okay, and I can say, okay, so let's look at some terminology that people keep saying, but it is actually incorrect. Okay, or I should say something that doesn't seem to be correct is actually correct. So I can say, okay, so by this time, I think if you have taken CISP430, you should have the class should have talked about different sorting algorithms already. Okay, so we got bubble sort, we got insertion sort, those are inefficient, and then we got bubble sort, we got quick sort, and so on, and those are efficient sort algorithms. Is that correct? Can I make that assumption?
Most
Yeah.
classes are on graphs right now, so we got heaps and merge already.
Okay, excellent. So now let's look at merge sort. Okay, so we look at merge sort. Okay, and I can now say tag says merge sort has a time complexity that is an element of big O of n cubed, where n is the size of array or number of items to sort. Okay, it doesn't have to be an array with merge sort. Okay, so now the question is this statement correct? Let me say that one more time. Okay, text says, okay, back grammar. Text says merge sort has a time complexity that is an element of big O of n cubed. The question is that statement correct?
N
It,
cubed is the upper bound,
Exactly. Big
so
O,
it's true.
it is true. Very good. Okay, this is true. Because all I'm trying to say is n cubed is an upper bound of the actual time complexity of merge sort as an algorithm. The answer is yes. Okay, absolutely. Because the actual tight bound of merge sort, the time complexity of merge sort, is n log n, okay, which grows relatively slowly compared to n cubed. But big O really is just talking about the upper bound of time complexity. It is not a tight bound. Okay, it can way overshoot. Okay, because it can just say, I'm just gonna say, to be safe, I will say the upper bound of this algorithm is blah blah blah, and that blah 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 is way overestimating the actual time complexity. But it is still true. Okay, this statement is still true, even though it is not very useful. Okay, just because a statement is true doesn't mean it is useful at all. Okay, because instead of using n squared, I can even n cubed. I can make this even worse, right? I can say this is big O of n factorial, because n factorial grows way faster than n cubed. Okay, but it will still be true because hey, this is a even it's a loose, it's a very 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 loose upper bound. But that doesn't is not useful at all when we need to look at the actual realistic time complexity and compare algorithms, because almost all every single sorting algorithm, like bubble sort, insertion sort, every sorting algorithm is going to be an element of big O of n factorial. So that means, then how do we compare? Because they all have the same upper bound. So just knowing the upper bound is not enough to say, okay, now we have to choose this algorithm over the other one because this one has a better time complexity. Nope, we have no information whatsoever because we are just using a very very loose upper bound. We are running out of time today. Okay, I still got 1 minute or so. But I want you guys to read on, okay, because we have just dug through the really difficult part of this entire module, okay, which is the definition of limit superior and the limit inferior using Infinum and Supremum as the quote unquote sub definitions. But from this point onward, okay, we are basically just looking at the upper bound and also the lower bound. There's also such a thing called negligible, okay, which is not really useful. Okay, negligible is basically saying that something is a gross overestimate. Okay, so n factorial is a gross overestimate of the time of the actual time complexity of merge sort. So it's not really that useful because it's gross overestimate. So we want to know what is an upper bound. We want to know what is a lower bound. Now, when we have a tight bound, which is in the notation of big theta, that means a particular function is both the upper bound and the lower bound. Now we are talking about something that is actually useful, because when we find the tight bound of the time complexity of an algorithm or two algorithms, then we can finally compare those two and say, okay, we look at this, we look at this, how do they compare? Okay, so we are out of time today, but I do want to kind of encourage all of you to read the notes, um, finish this entire module, and bring your questions on Thursday if you have any, because these notations can be tricky to understand. So what you need to do is to write down the actual your understanding of these terms. And I'm going to upload what I have captured today, in what you see over here. Okay, but on the tablet it's actually captured, on three separate pages, and I can just upload it to today's channel. Do we have any questions before I end today's lecture?
What was your dissertation on?
My dissertation? Okay, I don't think we can find it online because this is before people start to post things online, but I can type the name of the dissertation if I remember correctly, but I think I do.
You can find fossils.
Well, it has been a long time. I mean, it has been 25 years since it is done. It is stochastic admissible heuristic search. That was, I think that was
Uh,
the title of the dissertation. It only had 60 pages ish, to begin with, um, because it was basically, I was just proving the properties of a solution to a problem where the state transition is probabilistic. Um, and then the professor said, well, you cannot just have you cannot have one single proof as your dissertation. You need to use English. I go like, well, then what do I do with the formal proof? Well, you put it into the appendix of your dissertation. Then I go like, then I only have like 5 pages left. Then the professor said, well, you're gonna have to find a way to put in more content. In other words, I had to kind of fluff it up a little bit. Yeah, that was an interesting experience. There are even more interesting stories about my dissertation, but I can share those with you guys at the appropriate time.
Sounds good. Thank you, Professor.
You're welcome. Thank you. All right, so I'm gonna stop the live stream now and see you guys on Thursday. But I'm still on the text channel, so I will still be on the text channel.